Okay, hello everybody. I'm Scott Lathrop at the National Center for Supercomputing Applications at the University of Illinois. We welcome you to the second in a series of Blue Water's weekly webinars. Today's presentation is an overview of scientific workflows by Scott Callaghan, who's a member of the Southern California Earthquake Center team. And we're really pleased to have Scott join us today to give an overview of workflows. He's working using workflows as a part of his regular daily activities with his research activities. It's a pleasure to have you join us today, Scott. And if you're ready, we'll turn it over to you.
Great, Scott. Well, thank you for the introduction. I appreciate it. So yeah, as Scott mentioned, today I'm going to be talking about an overview of scientific workflows. I know that this is the first in a series of talks in the Blue Waters webinar about different workflow tools, but I know that it can often be overwhelming for people who are interested in getting started with workflows, but they don't necessarily know, what are the basic ideas, what should I be looking for when I'm looking for tools, how do I really get going? And so what I'm hoping to accomplish with my presentation today is to give you a little context, to give you some ideas of traits and characteristics that you can look for when you're comparing workflow tools, and ultimately to help you get started. As Scott mentioned, I use workflows on a regular basis in my research, and I found them to be really useful. And so what I'm hoping to do is encourage you to give them a try as well, because I think that really anybody who's doing scientific computing can benefit from workflow tools and technologies. So let me just provide an overview of the topics we're going to cover today. So I'm going to start by making sure we're all on the same page. What do we mean when we talk about workflows? What are the key elements that make up a workflow? So what aspects are common to workflows in general? We're then going to transition to talking about the tools a little bit. What problems are workflow tools supposed to solve for us? And what kind of things should you keep in mind when you're picking a tool for your own personal work? Last time I gave a talk like this, which was during a Blue Waters webinar back in the summer, one thing that people mentioned is they were interested in seeing, kind of going from the theoretical to how does an actual concrete application benefit from using workflow tools. And so I'm going to take a few minutes and talk about the application that I work on and explain some of the challenges that we faced, why we chose to use workflow tools, and how those tools helped us solve some of our problems, just to kind of give an example of how these things can be used in real scientific research. And finally, conclude with kind of a soft push as to why I think it's worth your time to give the tools a try. So workflows, what do we mean by that? Well, workflows are a formal way to express a calculation. And this calculation is basically consists of multiple tasks with dependencies between them. I use the word tasks vaguely deliberately because there are no limitations on these tasks, right? They could be short-running, they could be long-running jobs, they could be loosely coupled or even independent jobs, or maybe it's one large NPI job. Basically, anything that you can run on a computer is a task that can be put into a workflow. Workflows typically, in addition to capturing these tasks, they capture some information about these tasks, the parameters to the tasks, any input files that come in, output files that are generated. So these are also captured as part of the workflow. Typically, too, there's this concept of independence between the workflow process, so that is the algorithmic steps that you're going through, and the data that is being operated on. So you could think, for example, you might run the same workflow multiple times, but you might run it on different sets of data, right? So you can essentially reuse a workflow. Now, I would make the argument that even if you don't necessarily think of it this way, you are actually using workflows all the time in your everyday work. And let me give you an example of that. So let's take a look here at this dummy shell script. Right? We'll just kind of go through it line by line and see what we're doing. So in this first line, right, we're copying in, we're doing an SCP command. We're copying some input data in from a server somewhere, this hypothetical datastore.com server. And we're copying it into local Scratch. We'd like to run some applications on it, and so we need to have it in the local compute environment so that we can actually use this input. In workflow terminology, this is called staging in. It's when you copy data into the compute environment so then you can do something to it. Well, the second line, we're going to run a simple serial job, this pre-processing job. we're going to take this input file and we're going to produce some kind of temporary output file, which is formatted the way we need it to be. Next, we're going to run our big job. We're going to run a big MPI job here, parallel job. We're going to use this temp file as our input. We're going to produce a bunch of output files, say one per core, output.1, output.2, so on and so forth. This is kind of our big job here, step 3. Next, maybe we want to make sure that those outputs are okay. We didn't have some error in our MPI code. And so what we're going to do then, this is just a for loop in Bash parlance, so if you're not familiar with it, don't worry about it. But we're iterating over every output file, and we're going to run this integrity check job. Maybe we're going to make sure that the file doesn't have any nans or any zeros in it, for example. If you notice this ampersand here at the end, what that just means is we're going to background the process so we can run a bunch of these all at the same time. And essentially what we're doing here is we're doing scheduling by hand, right? We know that we can run all of these jobs at the same time because they don't depend on each other. And so that's what we're doing here. Well, while those are running, we'd like to capture some metadata. We'd like to remember when it is that we did this simulation because that might be useful to us later. So we're going to run a date job, grab a time step, and then we're going to merge all of our output files into a single output file and put the time step on the end. So that way, if we come back and look at it later, we know when we did this. Finally, we want to make sure we save that output. We don't want it to get purged in Scratch, so we're going to copy it back to our permanent storage for archival. And in workflow terminology, this is called staging out, when you have data that you would like to copy out of the compute environment and somewhere else for long-term storage. So I argue that essentially a shell script that looks like this is really just a workflow. Right? We could think of it as a flowchart, if that helps, and maybe that makes it clear that it's a workflow. Right? We have an input file, we staged it in, we copied it into the compute environment, we ran our pre-processing and reformatted it, we did our big parallel job and generated a bunch of output files. Then we ran integrity check on each of those output files, but we also ran date and merged those output files into a single file with a timestamp on it. Finally, we staged those files back out to long-term storage. So what are the key elements going on here, right? And when we start to think about workflows, and even something like this, which is in its own way a workflow, what are the key concepts going on here that we want to bear in mind? Well, the first is just we have task executions with dependencies, right? Every green circle here is a task, and the arrows here help to illustrate the dependencies. And so we see that we have to run, for example, the pre-processing before the parallel job, because the pre-processing produces an output file, which then serves as an input. Right? So we have this concept going on. We have the idea of task scheduling, right? It's not just that we run one task at a time, but for example, we can run the merge job at the same time that we run the integrity check jobs. And so we have this idea that there might be a certain amount of parallelism that's possible in our workflow. Another concept is what we call resource provisioning. And this is just the idea that there has to be a way for you to get compute resources, for you to go and get processors to run your jobs on. Right? If I have a job that I want to run, I have to be able to go and actually get cores on a system somewhere, whether it's my local machine or it's Blue Waters, and run my job. A couple more concepts are that of metadata and provenance. And so, metadata, right, is information about your run. So maybe, when was a task run, right? We saw we captured that in this sample script by grabbing a time step. And there might be key parameters and inputs, for example, maybe what was in that input.txt file. These are also things that we would think of as metadata, as information about a workflow run. The last concept that I want to pull out as a key element of workflows in general is the idea of file management. Right? Most of us are running workflows that involve files at some point, and we need to make sure that the files are in the right place at the right time. The input files have to be present in order for our task to run successfully, and when we're done, we probably have output data we'd like to save. Right? And so maybe that's publishing it to a website or just copying it out somewhere else. But regardless, there's this idea that we have input and output files that we need to keep an eye on and make sure are doing what they need to be doing and are in the right place at the right time. So these concepts all seem pretty straightforward, right? We have this little shell script that handles them just fine. So why would we need help, right? Why would we want to bring in an external tool to help us with some of this? Well, let's think about each of these categories. So we talked about task executions with dependencies. What happens if something fails in the middle? It could be hard for us to easily recover. Also, we can imagine that we might have workflows that are more complicated than this simple one. There might be a lot of tasks with complicated interdependencies, and it could be quite difficult to figure out how to run everything correctly. With task scheduling, we want to run our workflow as quickly as possible, right? We'd like to get our results, sooner rather than later. But we also need to make sure that we preserve any required dependencies, right? There may be reasons that tasks have to run in a certain order. And so it may start to get complicated as your workflow gets larger and has more tasks to figure out how to optimally schedule and run your workflow. There's this idea of resource provisioning, right? If I want to run my jobs on a remote system or maybe even across multiple systems, for example, I want to run some jobs on locally, some jobs on a cluster, and then maybe go and run some jobs on a visualization cluster. It could get pretty complicated in figuring out how to match my tasks to processors so that I can get the work done. We captured a little metadata and provenance here, right? But it would be nice to automatically capture more without having to explicitly run this, date job. And I might want more information than just what time did the task run, right? I might want to know how long did the task take, where did it run, what were the inputs and the parameters that I used to it, maybe even what versions of the code were used, right? If we're doing science, it needs to be reproducible, and so we want to be able to keep track of everything that I need in order to reproduce that information. Another topic is file management. So we need to make sure that the input files are there available for the tasks to run. And again, this can start to get complicated if you have more than just kind of one simple task. This is something that might become tricky to keep track of. And if you're doing this by hand, right, we've all made that mistake where you forget to copy in some input files, you run the job, it fails. And so it would be nice if we didn't have to worry about doing it ourselves. And this more generally is also something that we could use help with, right, is the idea of automation. So you, I would argue, have a workflow already, right? And it might look something like, maybe you run a script to reformat your inputs. You submit a job to the queue. You check the queue to see if the job is done. You check the queue again. You check the queue again. Finally, the job is finished, right? Maybe you copy the file somewhere else. You run some post-processing. You transfer it to a different machine, right? You have a process that you go through when you're running codes on systems. But oftentimes that process may have some manual steps in it, right? And every time that process has manual steps, this is a problem for two reasons, right? One is that it's taking a lot of your time, right? You're sitting there and you keep running, QStat or SQ or whatever to see how is my job doing, and that's time that you could be doing something else. The other problem is that you might find that the job finishes in the middle of the night, but you don't realize it until the morning, right? And so that's several hours when the computers could have been doing something useful for you that you don't have to be involved in. And so bringing in automation is something else that we could use some help with. I see there's a question on the Slack channel. The question was, what criteria, if any, should I take into consideration when deciding which tasks I should parallelize? So if you're talking about tasks at the workflow level, the good news about the workflow tools is they will help you figure out which tasks you can run in parallel. Right? Your job when you're constructing a workflow, and we'll talk a little more about this later, is to express what the dependencies are, is to say, task B has to run after task A. I know this because task A produces files that task B needs in order to run. But once you express your workflow, the workflow tools can go in and say, okay, we've analyzed your workflow and we figured out that this task over here and this task over here are not dependent at all. So we can run both of those at the same time. And so this is one advantage of the tools, is you don't necessarily have to yourself explicitly say, I can run these tasks at the same time. As long as you express your dependencies, the tools can figure that out. In general, I appreciate the questions on the Slack channel. I will try to answer them when I get to the end of the slide. But since I know that there's a little bit of a delay, it may seem like I'm waiting longer than you might want. But I will get to them, I promise. I do appreciate also questions during the talk are perfectly fine. I'll have some time at the end for questions as well if there are things you want to save up, but whether you want to ask them during or at the end is fine with me. So let's talk a little about these tools. Right? What do I mean when I say workflow tools? Well, I'm talking about software products that have been designed to help users with their workflows. Typically speaking, these products have two pieces. They have one piece, which is a component that allows you to create a workflow. Right? There has to be some way that you can tell the tool, hey, I want to run this code, and then this code, and then this code, and then this code, and here's how they're dependent. They also come typically with a second component, and the second component actually runs your workflow. So it's a component that says, I have sent this job to be executed. This job is finished. That job looks good. Now I can run this job. So that's the component that actually does the real-time running. You'll notice between different tools, these components have different names. They call them different things. But all the tools are going to have one component that helps you create your workflow, and then something else that will help you do the real-time running of your workflow. These tools can support all different kinds of workflows. Again, anything basically that you can run on a computer, you can put in a workflow. They can run at many scales too. They can run on your local machines, your local desktop, or your laptop, all the way up to the largest clusters that are available, to running on Blue Waters or the DOE systems, for example. They allow you to use your existing scientific code without making changes to it. These are tools that wrap around code you already have, so you don't have to worry about going in and making adjustments to your carefully tuned scientific code. They all bring automation to the process. Right? They all allow you to hit go and then have all of your jobs run, and then when you're done, you have your final data output products, right? So that's one of the big advantages that they all bring, is increase the level of automation. These tools individually, and there are many tools out there. I know as part of the seminar, I think 6 different tools are going to be presented, but that's honestly just a small subset of what's available. And they all provide many features and capabilities, usually all a little different, that's how they differ, for flexibility. I'm not going to get too much into these features and capabilities today. I'm going to let the individual tool developers talk about that. It can get overwhelming when you're trying to just kind of understand what's out there and get a sense of the big picture. It can get pretty overwhelming if you start to get into the nitty-gritty of all the tools. So today we're mostly going to talk at a higher level about some of the characteristics that differ between various tools to start to give you a sense of what questions you should be asking and what things you should be thinking about in deciding what tools would be best for you to give a try. So what problems do these tools solve for us? Well, if we go back to the list we were looking at before, for task execution, these tools will automatically retry jobs that fail. If jobs keep failing, then they'll write a workflow checkpoint. So when you resume the workflow, you can pick up from where you left off. The tools help us with data management. So they will automatically figure out what files need to be staged in and what files need to be staged out for jobs to run. And they'll ensure that all the data is present before a job runs automatically. So this is something that you as a human don't have to be involved in. The workflow tool is excellent at scheduling your tasks. And this kind of gets back to the question about which tasks can run in parallel with other tasks. They're very good at figuring out how can I run this workflow as quickly as possible, even given constraints, even given certain limitations of resources. They're very good at figuring that out. They're also excellent at capturing metadata. So they will automatically track stuff like runtime, what was in the compute environment when I ran this job, what were the arguments to this job, what were the inputs, what were the outputs. And so it makes it really easy if you need to go back and see what you've done to figure it out because of the things that the workflow tools will automatically capture for you. They also help you with this problem of resource provisioning. Whether you're running a small job on your machine, you're running a large parallel job on a big cluster somewhere, or maybe you're running a lot of small jobs, and so your goal is to get high throughput. The workflow tools will help you with all of these kinds of job profiles. So this is just an overview of the schedule for the workflow webinar. I think there's a possibility there may be future talks as well, but these are the ones which are currently scheduled. And so I'm hoping, as I said, to kind of give you an overview and help you get your feet wet and inspire you maybe to go to some of these other talks. And so the majority of these other talks are about specific tools that are written by specific groups. And so they'll get into some of the details about that tool. I believe the April 12th talk on computational data workflow mapping isn't a tool in particular. It's more about how to think about your process and think about how you would take it from what you have now and put it into a workflow tool, which is something that I think could be useful for a lot of you that are just getting started with this approach. But as I said, what I'm trying to do today is give you some criteria that you can start to think about in evaluating these tools. Because you want to go into kind of each of these talks with a basic idea of workflow principles and also some ideas what you're looking for your own computational needs. So that way you can bring that to the table, you can ask questions with that in mind, and that'll help you figure out which of these tools is worth you spending some time with. So now I want to transition a little bit, and I want to talk about those criteria. What should you keep in mind when you're thinking about how to select a workflow tool? Well, the tools that are going to be presented are solving all the same general problems, and these are the problems that we've mentioned earlier in the presentation. Where they differ is in kind of their specific approach. And I'm going to give you 4 categories that I encourage you to think about when you're evaluating tools for your particular scientific application. One is the interface. So this is how do you actually build your workflows. 2 is what we're going to call workload. What does your workflow look like? What kinds of jobs are you running? The 3rd category is that of the community. What specific computational or scientific domains does a tool focus on, if any? And lastly, we're going to talk about resource provisioning. How do you match resources to jobs? There are 2 ways you can do this. There's a push approach and a pull approach, and so I'm going to kind of explain what those are. So these are 4 things that you can keep in mind and can start you thinking about what tools would be best for you. And as you go through and you hear the talks, you'll find other points of comparison, but this is just kind of to get you started. So interface. So what I mean by that is, how does the user actually go in and tell the tool, these are the jobs I want to run? There are a couple of approaches. One way you can do this is graphically. But it's like assembling a flowchart, right? You put a box up here and then a box down here, and you draw a little arrow between them, and then you put a box over here. And so you just kind of make a flowchart, and that explains your workflow. Another approach is scripting. The workflow tool comes with some kind of specific scripting language, and you use this language to describe your jobs and how they relate. A third option is to use an API. So what you do is you use a common programming language, Python or Java or something like that. And the tool provides a specific API, so specific function calls. And you use these function calls to assemble your workflow. Right? Maybe you call one function to create a job and then another one to say that there are these dependencies. So which one's best? Well, it depends on you and your application. So the graphical approach has the advantage that it's very intuitive, right? It's really easy to make boxes and link them together. But if your workflow starts to have a large number of tasks, even hundreds maybe, it can become quite unwieldy to have all these boxes and arrows that are going on. On the other hand, it's easy to make a pretty picture, right? You can do a screenshot, you can show it to someone, you can say, this is my workflow. That's kind of the advantage and disadvantage of the graphical approach. The scripting and the API approaches can require more initial investment, right? You either have to learn a custom scripting language, or you have to learn a custom API. So that can take a little time. But if you have a workflow that has a lot of tasks, it can be a lot easier to manage that using this approach. Additionally, some people, once they've learned the new scripting language or the API, actually find it faster to assemble a workflow this way, because sometimes with the boxes and the arrows, it can get kind of finicky. So which way is better for you is up to you, but it's something you should keep in mind. Some tools support only one of these approaches. Some tools support multiple. For example, some tools have a graphical interface, but then if you prefer, you can write code instead. It's up to you. A second category to consider is that of workload. So what kind of workflow are you running? What are your jobs like? Are you running a large number of tasks, or are you running just a few? Are your tasks really short? Maybe they're a couple of seconds or a couple of minutes. Or are you running long tasks that are, hours or days? Your workflow, is it static? That is, when you start your workflow, when you run your first job, do you know all the jobs you need to run? Or might your workflow be dynamic? Maybe depending on the outcome of a certain job, that influences what jobs you're going to run next, right? Some tools do and do not support dynamic workflows, and so this is something that's good to keep in mind. Another thing that may seem trivial but actually affects the tool you might use is if you have loops or not. So for example, are you going to come down and rerun a job or jobs multiple times? Maybe you don't even know how many times you're going to run the job, because maybe it's iterative, right? You have to run the job until some parameter converges, and so you may not know when you start how many times that will be. On the other hand, maybe you do know. Maybe you can represent the workflow in what's called a directed acyclic graph. So you have, parents and then they have children, and then they have children, and so on and so forth, and there are no feedback loops within that cycle. And like I said, this might sound like a weird feature, but some tools do support loops and some don't. So it's good to think about whether or not this is a feature you need before you pick a tool. The third category I'm going to present for consideration is that of the workflow community. What kinds of applications is the specific tool designed for use with? Some tools focus on certain science fields. It's not that they're exclusionary, but it's that they have a certain area where they've put a lot of their effort. They've probably tried to recruit users from that area, and they may have also modified their tool to have certain features for people from that area. So for example, maybe there are certain paradigms that are unique to your science domain. Well, those might be built into the tool. Or maybe there are task types. For instance, I know there are some tools that focus on, have an emphasis on statistics. And so they have a lot of built-in jobs that automatically do certain kinds of statistical analysis. And so you don't have to go off and find your own. You can just use what's in the tool already. Another feature is that the workflow community in this case may mostly be in your science area. And so that could be helpful. You might be able to use workflows that someone else on this tool is already using because they're doing maybe similar processing. If you have questions, you might not have to explain quite so much what it is that you're trying to do. The downside, of course, is that if the tool is in one field and you're in another, then maybe it will be less useful. Or it may be that the special tasks or special approaches that the tool has built in for you aren't actually useful for you, right? For example, maybe its focus is in bioinformatics, but you're doing a slightly different kind of work, and so the bioinformatics tools that are built in aren't really useful to you. In which case, the advantages of the tool being in your domain maybe are diminished. There are, of course, tools that aren't focused on a specific science domain. And so these tend to be more open-ended. They may come with fewer task types built in, but they may be very flexible when it comes to bringing in your own tasks. They have a community that's also usually less domain-specific. The disadvantage, of course, is you might have to explain in more detail scientifically what you're doing, but you might find that you have a lot of computational similarities with someone, right? It may be that you need to run a lot of tasks of one type. They're all running, maybe you're running a lot of bioinformatics tasks. They're running a lot of astrophysics tasks, but you're both running a lot of tasks. And so you have a lot in common and you can share information that way. One of the things that I encourage you to do, if you have collaborators that are using workflow tools, I encourage you to reach out to them and say, okay, what tool are you using? Why did you pick that tool? What do you like about it? What do you not like about it? And that can be a good jumping off point for finding out what tools are being used in your community and figuring out if you want to also use those tools or maybe try something different. The last category I want to talk about gets back to this issue of how to take your work and put it on a processor somewhere. It's obviously really important to automate this, right? A big portion of why we're using workflows is this idea that we can hit go, that we can run everything, and that when it's done, we have our final output data. But if we have to be involved in that, if we have to, for example, SSH into Blue Waters every time we want to run a job on Blue Waters, then we lose our advantage, right? If we have to do that, then we lose the automation, and that's not so good, right? It's not as we lose a lot of the benefits of using workflow tools. So we need to come up with an automated way that we can take a workflow description, which might be on our laptop, and send the jobs off to Blue Waters or whatever cluster you like to run. Well, there are two basic ways you can do this. One is what we call a push approach. So the idea is when you have work you need to do, you then go off and send it to the remote compute resource. It runs, it produces its outputs. This is an approach we're all pretty familiar with, right? Every time we write a batch script, a PBS or a LSF or an SGE batch script, this is what we're doing essentially, right? We have work we want to do, we put it in the script, we put it in the queue, the job runs, the work is done. Okay. So this is one approach. But it turns out there are other ways you can do this. And so the other option is what we call a pull approach. So first what you do is you gather resources. You go off and you get processors or nodes. Once you have those nodes that are yours, then you say, okay, let me go get some work and put them on the nodes to run. This might sound weird, but any of you that have run using an interactive mode on a cluster have done this, right? If you run an interactive mode, what you're doing is you're going and you're getting your resources first. Once the resource starts up, then you say, okay, I have some jobs that I'd like to run on it. So these are the two options. Which approach is best for you depends on your workload, but also on the system that you're targeting, because not all systems will support both approaches. I'm going to get into a little more detail about both of these here. And I want to show you this because this is something that it's worthwhile thinking about and thinking about what might work on the systems you want to use. That way, when the tool developers are presenting their tools, you can say, hey, I have a question I'd like to run on this system. I think I need to use a pull approach. How does your tool support that? So let's talk about the push approach first. On the left here, we have running on maybe a local system somewhere, we have the workflow tool. So it's keeping a queue with the jobs that I need to run in order to do my workflow. I've got task 1, task 2, task 3. So with the push approach, I say, okay, task 1, I've got work to do. I'd like to go run it somewhere. So I'm going to go off, and I'm going to submit it to the remote queue on the cluster somewhere. So that's the first step. We wait for the job to run. Eventually, the job gets scheduled. It runs. When the job is done, it calls back to the workflow tool and says, hey, task 1 is complete. And then the tool says, great. All right, task 1 is done. Now I can schedule task 2. It's pretty simple. It's pretty straightforward. So the advantages of this approach are that one is there's very low overhead, right? We're only using nodes when we're getting work done, right? The only time we're running on a node is when we're running task 1. That's very good. However, we don't know how long we have to wait in the queue, right? Task 1 might wait in the queue for a minute. It might wait in the queue for a week, right? We don't necessarily know how long it's going to take before our jobs run. The other thing that's really important here, and that maybe doesn't seem important but is key, is this link 1 here, right? We have to be able to do this. There has to be some way that we and our workflow tool can send a job across the network and put it into the remote queue on another system. And so in order to do this, the remote system has to support it. The remote system has to be okay with you using some kind of authentication technique that is automated, like SSH keys or proxies or something, right? If you had to sit and use your fob for two-factor authentication every time you wanted to do this, we wouldn't get the benefit of the automation, right? And so many systems, XSEED systems are particularly good at this, support this push approach where you can send jobs across the network and put them in the queue. But some systems, especially systems with tighter security restrictions, such as the DOE systems, don't support this. And then you have to use another approach. I see I have another question on the Slack channel. The question is, how difficult or easy is it to adapt for other workflows? And so I'm guessing what you mean by that is if you want to switch between different workflow tools, how easy is it to take your workflow from one to another? It continues with e.g. applications outside of the scientific domain, for example, text analysis. Sure. So what we're talking about today, we all have in common that we're running scientific applications for the most part, but the things that we're talking about today, there's nothing here that's unique to scientific codes, right? The workflows in general and the tools that we're talking about support any process where you want to run multiple steps and you have dependencies between them. So if it is text analysis or some other application that isn't strictly in the science domain, totally fine, right? All you have to do is to be able to say, these are the jobs I want to run. These are how they're related. And these tools can handle that. I'm kind of assuming for today's discussion that we're all interested in running on open science systems for the most part, that we're interested in running on XSEED systems or DOE systems or local university systems, just because those tend to have things in common. But I don't think there's much we're talking about today that's dependent on it being a scientific application. So the short answer is, I think what we've learned today, and hopefully what I'm communicating today, is applicable regardless of the content of your workflow. So we've talked about the push approach here. Let's talk about the other option, the pull approach. So again, we have over here on the left, we have my workflow tool, which is running on a system somewhere. I've got my queue with jobs. You notice here, though, I have a new element here, a new piece that's running called the pilot job manager. And we'll show you here what that does. That actually kicks off your process. Remember when we did push, we started here by submitting a task. Here, though, we start with a pilot job. And so the pilot job manager submits a job to the remote queue, and that job says, hey, I need nodes. So the pilot job starts up and runs, but it's not running any work yet. right? All that we've done here is we've grabbed a chunk of nodes and said, okay, we're ready to run. That job now calls back to the workflow scheduler and says, hey, do you have any work to be done? Scheduler says, I do actually. I have task 1. Task 1 would love to run on your nodes. So task 1 gets assigned to the pilot job. It runs and it finishes. Right? It may be that if there's still more time on the pilot job, for instance, maybe the pilot job is running for 24 hours and task 1 only took 1 hour, then the pilot job will call back and say, hey, task 1 finished. I'm free again. Do you have more work for me? The scheduler might say, yeah, here, let me send you task 2. Right? So the pilot jobs give you more flexibility in that sense. You can tailor the size and length of the pilot job to whatever meets the needs of the cluster. I mention that because some systems, for example, actually favor larger jobs. And so you might submit a really large pilot job to that queue, and when it starts up, you might say, I can run tasks 1, 2, and 3 all at the same time on the same pilot job. So it gives you some flexibility that way. The downsides of it are that you have more overhead, right? The pilot job might run for a while before you have any work, but you're still using cycles, you're still using compute time, you're just not doing anything useful with it. You have a little more complexity, you have this new component, but it is more flexible. The pilot job manager, as you see in this example, can actually run on the remote system. You don't have to worry about that number 1 link that we saw here, sending jobs from the workflow tool to the remote system. It's all done locally. And so again, I mention this because it depends on the system you want to run on. Some systems will support that remote job submission, some won't. I, in my work, have run on both systems. For example, I've run on Blue Waters and Titan. Titan is one of the machines at Oak Ridge. It's a DOE machine, and so they have tighter security limits. And so for Blue Waters, we ran using the push approach, and on Titan, we ran using the pull approach. So, like I said, it depends predominantly on what systems you want to run on and kind of what your work looks like. Anyway, I want to put this out there because this is something, some tools will support one approach, some will support another, some support both. But this is something to keep in mind because, if you're running on a system that only will support the pull approach with pilot jobs, you need to make sure that the tool you're using supports that as well. So we've talked somewhat theoretically about the advantages that workflow tools have, how they help researchers and other people using workflows, and some of the things that might differ between various workflow tools, topics to keep in mind when you're picking a tool for yourself. But let's take a look at a real scientific application and say, okay, why did you use workflow tools and how concretely did they help you get your work done? So just for a little bit of background of the science that I do, let's say you're interested in building a building in downtown Los Angeles. You want to build a big, tall skyscraper. You want to know how strong to build this building, right? You know earthquakes happen in Los Angeles, and so you've got to make sure that the building will stand. This is obviously something that's important to get right. If you overestimate how strong your building needs to be, then you run over budget on the building. If you underestimate, then the building may fall over, right? So something you've got to get right. And so we asked this question then, what is the peak seismic ground motion for downtown Los Angeles, for my hypothetical building, going to be in, say, the next 50 years, roughly the lifespan of the building? And this isn't just used for buildings, this kind of information, but it's also used for setting insurance rates or for determining emergency response priorities. So to answer this question, we can use a technique we call probabilistic seismic hazard analysis, or PSHA for short. Basically what we do is we look at downtown Los Angeles, we go out about 200 kilometers, and we gather all the possible large earthquakes that might happen. It usually is about 500,000 earthquakes of magnitude 6.5 or greater. We simulate each earthquake individually, and we then, from each earthquake, get measures of shaking, and we combine that shaking measure with the probability that the earthquake will occur. And we produce what we call a hazard curve. You can see one down here on the right. And the software stack that we use to do this, we call the CyberShake platform. That's what we call kind of the whole suite of codes that's needed to do this. And so once we have one of these curves, we can answer our question about the building. We can say, all right, let's look at the 2% and 50-year chance. This is a typical level used for buildings. So this is saying, there's a 2% chance in 50 years of how much shaking. We say, well, it's 0.4 Gs, so we make sure our building is that strong. If we were going to build a hospital, we'd go down further on the curve. If we were going to do a nuclear power plant, we'd go down even further. Right? It's obviously a probabilistic estimate because you can't be deterministic about these things. All we can do is give you some probabilities. So computationally, what's involved in making one of these curves? Well, we have both large and small jobs. We have to run two large parallel jobs. And so for us, these are jobs that run on GPUs. They're wave propagation jobs. Each one takes about an hour on 800 nodes and produces a total of 1.5 terabytes of output. We also have to run a bunch of small serial jobs. Remember I said there are 500,000 individual earthquakes? We have to run a small calculation for every single earthquake. So there are 500,000 jobs we have to run. These jobs are small. They're serial jobs. They take about 5 minutes to run on average. But the challenge is, again, that there are 500,000 of them, right? In total, they produce about 30 gigabytes of output. There are a couple of other jobs too, but computationally, they aren't very demanding. And so these are the two kinds of jobs that really drove our concerns when we were trying to figure out how we're actually going to do these CyberShake calculations. In addition, these numbers here are what you need to get a single curve, right? A single curve you see here down on the right. We're typically, though, interested in the hazard for a whole region, right? We're the Southern California Earthquake Center. So as you might imagine, we're interested in the hazard for all of Southern California. And so we have to run about 300 individual curves in order to get enough density of locations that we can produce a map and understand hazard for a whole region. So, 500,000 jobs times 300 is a lot of jobs. And so this is one of our big challenges, is how we were going to run all of these calculations and get them done in a reasonable period of time. So what specifically were the challenges we were worried about? Well, one was automation, right? This is just way too much work to do by hand. You've got all of these jobs. You're trying to do them for 300 locations. There's no way that someone can sit there and individually write and submit scripts for each one. Like, that's just not going to happen. The second challenge was data management, right? If we have 500,000 jobs, it's a lot of input files. We got to get all the input files into the right place at the right time. Then we have to copy all of the output files when we're done back somewhere else because we need to archive them for long-term storage. Another big challenge we were worried about was resource provisioning. How do we take all of these little jobs and move them individually through a supercomputer, right? Supercomputers aren't really optimized for lots of small jobs, so how are we possibly going to do that? Another thing we were worried about was error handling. Whether it's the big jobs that fail or the little jobs that fail, how are we going to handle that, right? If 10 of these 500,000 jobs fail, how do you find those? How do you fix it? How do you recover without this just becoming an overwhelming task for, a researcher, for me? So these are the challenges that we were facing in trying to figure out how to make this calculation on paper a reality. So we decided to use a particular tool, which is called Pegasus WMS. This is one of the tools that is going to be profiled, I think, in May. They're doing one of the presentations. So I'm not going to go into details about Pegasus because that's not the goal of what we're talking about here today. But I do want to mention, based on those criteria we saw earlier, why did we decide to use Pegasus? So one is that Pegasus uses an API for a workflow description. This was important to us because we had a large number of tasks. It was going to be very unwieldy if we tried to do it graphically. So we needed something where we could write code to describe our workflow. A second reason that we chose it, the workload issue, is that Pegasus is good for supporting lots of different kinds of tasks. It's very flexible. Pegasus doesn't support loops. You have to have just parents with children, with children, with children. But we don't have any loops in our process, so this was not a limitation for us. Pegasus is not specific to a certain domain. There's a general community that uses it, but they all tend to run on large clusters. We were also interested in running on large clusters, so this was an aspect of the community that appealed to us. It meant that they dealt with a lot of interesting scalability challenges already. Pegasus supports both the push and the pull approaches, and so we knew that we were going to be running on a number of different systems, some of which would support one approach and some of which would support another, and so it was important to us that both approaches be supported. Another factor in why we chose to use Pegasus, and I didn't mention this in kind of 4 criteria, was that Pegasus is based at USC also. Where are you based at USC? USC ISI, which is another division. And so partially because of that, but partially also because they're good people, they provided really excellent support. And this is actually something that I think is really important. When you pick a tool, make sure that you're going to get good support from the tool developers. whether it's the user community or it's the developers, because the user community also can provide excellent support with experiences that they'd had. I think that's really important because you're going to run into some problems and issues. And honestly, in my experience, the biggest reason that people don't use workflows is because they try it, they run into a problem, they ask for help, or they don't get an answer, or they don't even know who to ask for help, and so they give up, right? Because they're stuck and they don't know what to do. And so I certainly encourage you that when you pick a tool, to make sure that the tool has good support, because being able to ask somebody for help and get responses just really makes your life easier and really helps you, kind of finish the process of setting up the tool. It really helps you actually have a workflow that you can use. So these are the reasons we chose to use Pegasus. Like I said, it's certainly necessarily not the best tool for everyone, but it was a good fit for us. So we use the Pegasus API to write a workflow description. So I use Java because we started this back in 2007. If I was starting it now, I think I'd use Python. And so there's a series of function calls. We say we want to run this job and then this job and then this job. You then with Pegasus do what's called planning the workflow to run in a specific system. You basically take your workflow description, the description of your algorithm, and you put in the specific paths to the actual executables on the system you're running on. And then the component that runs the workflow, remember I said typically there's a component that helps you create your workflow and then a component that helps you run it. The component that helps you run the workflow for Pegasus is a tool called htcontrol. Pegasus doesn't require any modifications to scientific codes, and this was something that's always been very important to us, especially to me. I'm a computer scientist by trade. I'm not a seismologist, and so I get the codes from the seismologists and I integrate them. But I want to make as few changes computationally to those codes as possible, because every year or two I get new versions of those codes, and if every time I had to add back special custom changes, it would be a nightmare. So I've appreciated the fact that I don't have to do anything to the codes. I just put the codes in the workflow, and then the workflow handles them and runs them. There's just a question on the Slack channel. I'm going to make sure that it's been answered. Okay, let me take this one. So the question was, if we already have a script to generate the large number of serial jobs, like your small jobs of one core, will this need to be recoded into the workflow package, or is there a good way for the workflow software to integrate that script? And then it was clarified that these tools have something which allows for an integration of scripts that already do some of the workflow, but still do failure check, cleaning, etc. So since anything that you can run on a computer you can put in a workflow, you could, of course, just drop your script into the workflow, right? The reason that you would do that is if you didn't necessarily need any of the advantages that the workflow tools brought to your to that script, right? If that script was good and that was all you needed, then that's fine. I have, for example, some wrapper scripts for some of the codes that I run, because I take some parameters, I set up a couple of input files, and then I run that. All the workflow knows about is the wrapper script. However, I'm actually going to talk in a couple of slides about how the workflow tools, how Pegasus helped us run a large number of small jobs. And so what you may find is that the tools have some clever things that they do to handle a bunch of small jobs that you may want them to do rather than handling it yourself. So I'm going to talk about it, and if you still have a question about it afterwards, Edward, please ask again in case I haven't addressed it. So what are these solutions that Pegasus helped us apply with the workflows? Well, one was automation, right? Using workflows meant that all of these jobs are automatically submitted. So literally, I hit go, everything that needs to run is run. When it is done, I get that curve. I get a nice PNG file with that image of that curve that I showed you in the beginning. All the files are transferred, everything is done. And so that's been really nice, right? Having that degree of automation, that I don't need to do anything by hand. A second thing that has been helpful is the data management. Pegasus automatically added jobs for us to transfer in all of our input files to the system and then transfer all the output files back to local long-term storage. Pegasus also will support, running, and this is true of most tools, you can run workflows on separate machines. So there have been times when we've, for whatever reason, wanted to run the large GPU jobs on one system, but then run the 500,000 short jobs on another system. And so Pegasus will automatically say, oh, these are running on separate systems. I need to copy the files from this system to this system before I run these jobs. And again, it's lovely that these things are handled automatically, right? You just human doesn't have to be involved, and that makes the process much more efficient. You can also use Pegasus to clean up intermediate data products when they're not needed. That's been nice because we generate a lot of data, and so we worry sometimes about going over quota, right? So if things are cleaned up as they're used, then that's also something that you don't have to do by hand. You don't have to worry about accidentally deleting data that you needed later, but you stay under quota, and so it makes you a good user, and it also just prevents things from running into a screeching halt. I mean, I know that I've done it, right? I've run over quota, and then suddenly everything stops running. You say, what is the problem? Why is this broken, right? So these tools help you prevent that from happening. The other big challenge for us was resource provisioning, right? How do we get the 500,000 jobs to run on systems? And I think this maybe gets into a little bit of Edward's question about, do you want to break down the serial jobs yourself or have the tools do it? So Pegasus in general uses other tools. Part of Globus called Graham is one of them for handling the remote job submission. As I said, it supports both push and pull. When you're running large jobs, this is easy. You have a GPU job, 800 nodes for an hour, submit it to the Blue Waters queue, it waits its turn, it runs, it's all good. But what about these small jobs? Well, I just want to mention here two approaches, both of which are supported by Pegasus, and both of which we've used at various times. One is to cluster. So what Pegasus will do is it will take, groups of jobs, groups of your tasks, and it will cluster them into a single job to run on the remote system. So for example, you might say, I want to take a packs of 5,000 tasks and group them into a single job. So now instead of having 500,000 jobs, I only have 100 jobs. Then I send these 100 jobs off to Blue Waters to run. This is obviously a great improvement to the remote system, right? You can't submit 500,000 jobs to a cluster scheduler, right? Most places, the cluster scheduler won't let you do it. There's a limit of maybe 50 jobs that each user can have at the same time. Even if it will let you do it, if you tried to submit 500,000 jobs, you'd probably crash the scheduler. It's just not handled for that kind of load. So using an approach like this clustering helps you get all your jobs done, but they appear as a single job to the remote system. So one job starts up on the remote system, it runs 5,000 of your tasks, but it only thinks it's one job. So you don't have this issue with getting jobs through the scheduler. Another feature that Pegasus offers, which we've taken advantage of, is an MPI wrapper. So what you can do is you can tell Pegasus, hey, I'd like to run these 500,000 jobs using an MPI wrapper. And so what Pegasus does is it takes your list of 500,000 tasks, it starts up an MPI job on the remote system on, say, Blue Waters. So say it starts up a job that's going to run on 1,000 cores, right? Core 0 becomes the master process. It takes the list of tasks and it divvies the work out to the 999 workers. Each worker works. When it finishes, it calls back to the master and says, hey, you have more work for me? And the master says, yep, here's another job. And so it will go through the entire list of 500,000 tasks this way. But Blue Waters just thinks it's a single MPI job, so it fits really well in the cluster. And it's also really, really fast, right? You're doing all of this inside an MPI job. There's very little overhead. It moves through really quickly. So this is another approach which we found really useful in going from our list of tasks to actually getting this to run quickly on a remote system. And I want to emphasize again that both of these features are just options in Pegasus, right? We didn't have to change anything about our work, about how our tasks looked, about writing this MPI wrapper ourselves, right? All we said is, hey, can you run this in this MPI framework? And Pegasus said, yep, I got it. I will go off and do all of the setup, all of the things you need. I have already written the MPI job. All I need from you is your list of tasks, and then I can do the rest of it. And so having these kinds of features have been really useful. This is another example where excellent support from the group has been really helpful because some of these features were specifically written by the Pegasus group to support our workflows. And so that's been a big help for us as well. I mentioned error handling. So if errors occur in our workflow, then jobs are automatically retried. If errors keep occurring, then as much of the workflow as possible will run. So for example, if 10 of the small jobs fail, 499,990 will run successfully. And then a checkpoint file is written saying, hey, the workflow failed, but when it resumes, you just need to rerun these 10 jobs. The rest are all good. So that's been a big help, both for identifying the failures and also for not redoing work that's already good. You can also, we haven't used this feature, but there's a way you can provide alternate systems. So you can say, well, if jobs on Blue Waters keep failing, maybe there's something weird with Blue Waters today. Why don't you try to run this job on Stampede instead? So that's also a feature that some of the tools will provide for you. Lastly, another benefit that we got from these tools is that using a workflow framework makes it really easy to add new verification jobs. So we were running a lot of files. We had hiccups sometimes. So one of the things that we did is we added, we wanted to do things like check for nans, check for zeros, make sure we have the right number of files, make sure that all the values are within a scientifically reasonable range. And when you already have a workflow, it's really easy to just, you write a little code that does this, and then you just drop it in your workflow. Now, every time we run the workflow, these checks are done automatically. If there's a failure, it'll be like, there's a problem. But most of the time, it runs smoothly. But we have that check in there, so we're able to detect problems right when they occur. One of the things that often comes up is a concern about scalability. Do these workflow tools really scale to run large codes? So I just wanted to take a moment and illustrate that for us, we've seen great scalability success. We started using workflows with CyberShake in 2007, and since then we've run on 9 different systems. So we've been able to take the same workflow and move it from system to system very effectively. The first time we ran it in 2007, we ran it on 200 cores, and we were really proud of ourselves. Most recently, we've run it on Blue Waters and on Titan. We averaged running on 55,000 cores for 35 straight days. How do you run for 35 straight days? Well, that's where the workflow tools come in, right? Because there's just no way that you as a human could do that. We hit a maximum of 238,000 cores, which was 80% of Titan's system, all done with the workflow tools, all handled by that. We generated 340 million different seismograms, but we only ran 4,300 jobs. So this is an example of how you can take your work, but the workflow tools can help you shape that work into a way that it fits really nicely onto the remote systems. Pegasus handled 1.1 petabytes of data for us. It transferred 408 terabytes automatically between Blue Waters and Titan intermediate data products, and archived 8 terabytes for long-term storage. So I just leave these numbers up here as an illustration that these tools really do scale. So why should you use workflow tools? Well, as I mentioned, I think you're probably using a workflow already. I think you already have steps in your process and a process that you go through, but some of those steps might be manual, right? There might be a human in the loop. Some of those steps might just be you checking queues to see if jobs are finished. The workflow tools are great at automating all this for you. They scale well from your local system all the way up to the biggest clusters you can get your hands on. They provide a portable description of your algorithm, which is independent of the data, right? It's a description of all the steps in your process, which are easy to move from machine to machine and to use to help others. I'd also say that the people developing these workflow tools, there are a lot of smart people that have been working on these problems for a long time, a decade or longer for some of these tools. So they've identified and fixed a lot of problems that you don't even know exist. And I think that you'll find as you start to write your own scripts, maybe your own Python scripts or whatever, to start to try to workflow the things that you already have, you'll find that you're reinventing the wheel. You're trying to come up with solutions to a lot of solutions that the workflow tools already have built in. So rather than trying to figure these things out on your own, trying to figure out how do I enforce dependencies, how do I deal with error recovery, all that, this has already been done. Take advantage of the tools that have already been written. So kind of for final thoughts that I'd like to leave you with, based on my own personal experience, I've been using workflows, as I said, since 2007. So I've been working with these tools and using them to help us get our science done for 10 years. And I honestly feel that there's no way that we could run CyberShake, that we could do the science that we want to do without having these tools at our side. One of the things that I would say that I've learned is that automation is really vital, that any human step starts to become a bottleneck as you try to scale up. So put everything in the workflow. Put validation jobs you might have. If there's visualizations you want to generate, put those in the workflow. You want to publish stuff to a website. You want to send an email notification to someone to say a job is completed. Put everything in the workflow, right? Otherwise, anything you have to do by hand becomes a bottleneck. It really is worth the initial investment. I'm not going to lie. There's absolutely an initial investment, right? You got to go in. You have to spend time learning the tool. You have to figure out how to describe your workflow in that tool. Probably some debugging. Might have to ask for some help. But once you've done that initial investment, right, there's very little upkeep. It's really easy to add new jobs, and you keep getting these benefits every time you run it. So I definitely encourage you to give it a try. Having a workflow provides some other benefits that are not initially obvious. One is it's really easy to explain your process. You have your workflow. You have your description. right? You can make a little flow chart with it. You can put it on posters. You can use it to train new people. You can say, okay, I want to explain to you how we do it. Well, these are the steps that we run, right? It's very easy to show people when you have something like that. These are the steps that we go through in order to do our work. It's also easy to take that same description and move to a new machine because you're running the same codes on the new machine, right? The only thing that's different really is the paths. And that's a small thing, and the workflow tools are set up to help you with that. But you're able to take the same description and move it from machine to machine to machine. Lastly, I'd tell you that the workflow tool developers really want to help you, right? I mean, you look at the fact that 6 tool developers are going to have webinars, right? Because they're really eager to have new people use their tools, and they want to support them. So when you try a tool, if you run into a problem, I encourage you to reach out and ask the developers for help. In my experience, they've always been eager to help new individuals. And honestly, if you run into problems, feel free to email me as well. I know some of the tool developers. My email's on the front page of the slides, and the slides are posted. And I'm happy to try to connect you with people that can help you resolve your problems. Just to conclude, I have a list of some resources here. There was a workflow workshop in 2016 that Blue Waters hosted, and all the slides from those are up. Those also included presentations from a variety of workflow developers. The 6 here also are the ones that are currently scheduled for presentation. I'd encourage you to go to them. I think they're each only an hour. And ahead of time, go to the website and do a little poking around. Now that you have kind of a sense what we mean by workflows, what some of the things are that differ between tools, if you go and spend a few minutes looking at them ahead of time, I think you'll be able to come into the sessions, ask some intelligent questions to understand how this tool might or might not serve you and your application well. Well, I appreciate the invite and the opportunity to speak at the webinar today. Now I'll hang out if there are any questions.
Well, thank you very much, Scott. We appreciate the tremendous presentation, and we encourage people to continue to post questions to the Slack channel now while Scott's still on or afterwards. And as he mentioned, you can email him directly as well if you have questions.
Absolutely.
So please join me in thanking Scott for a great presentation. I don't see any questions coming in, do you?
I see one, yeah.
Oh, go for it.
So the question was, for smaller workflows, i.e. 100 jobs, would you recommend using workflows? So I would say yes. There's, even with 100 jobs, and I know it depends on exactly which ones can run in parallel and all of that, there's still usually the opportunity for a lot of complexity. You still have input and output files to manage. You still have the error recovery. You still have all of these features. You don't necessarily have to be running millions and millions of jobs in order to see benefit. In fact, we certainly get a lot of benefit in our application from using workflows with, even just the large jobs that we see in the beginning. So I think it's certainly worth taking a look at, even if you're running workloads that are in the order of 100 jobs. The other thing that's nice too is once you've automated it, maybe you want to do a parameter sweep, or maybe you need to run the same workflow a bunch of times with different parameters. Once you've got it in a workflow, it's really easy to then just fire off 10 of them, right? And let them do their processing. Let them use the computer time.
Are there any other questions from the audience? If not, while we're waiting, I'll just mention that next week, the next presentation on Wednesday will be on Visit, the scalable HPC visualization and data analysis. And then 2 weeks from now, we'll be in the next workflow presentation by Nate on Makeflow and WorkQueue. With that, we'll wait and see if there are any other questions, but appreciate the thanks from the community for Scott's great presentation. Any final words, Scott?
I hope that you found this helpful. As I said, my hope is to encourage you to go off and try some of these tools. At the very least, I hope you're thinking about maybe attending some of the presentations that are continuing in the webinar, and that maybe you have a little better sense what people are talking about when they're talking about workflows.
With that then, as soon as the YouTube recording is available, which should be by tomorrow, we'll contact everyone who registered for this webinar. You have the slides accessible to you already from the website, and we will ask you all to complete a very short survey question. We'll send that to you at the same time we announce that the recording is available for you to view. With that, we thank you all. We hope you'll join future webinar sessions. With that, thank you, Scott, and have a good day, everyone. Bye-bye.
Thank you, Scott.
Take care.